minimize, we will just define this model H, which depends on the dataset, to be the model that will minimize the empirical risk, this formula. So HS is the empirical risk minimizer. And the main question in machine learning that a lot of persons studied and try to solve is the empirical risk evaluated on the best model that I have found on my training set. Does it generalize well to any example in the universe? Are these two quantities really different, or they are very similar? Can I hope to just find the empirical risk minimizer here, HS, and believe that it will generalize to any examples in production? And the main difference is these two things here. So let's begin by a simple model, which is not deep learning at all, and it's an optimal predictor. It's a lookup table. It's the most simple model that you can think of. I will receive a new image, like say X. I will look in my training dataset if this image is in the training dataset. If it is, I have the label because it is in my training dataset. So this lookup table will just return the label from the training dataset, if it exists. Of course, much of the data points are not in my training dataset, so I must return a default value, and here I will just return 0. So let's see a simple example in 2D. So here I have feature 1, which is between 0 and 1. This axis is feature 2, also normalized between 0 and 1. The green area here are points that are labeled to 0. And the yellow area here are points that are labeled to 1. And I have 6 data points in my training set. So this is a true data distribution. It's the D that usually for real data we cannot have. Here, because it's a toy example, I just make it for the exercise. We know D, so we are able to compute the real risk. And we will see how the lookup table performs on this problem. So remember, if the point is in my training set, I can retrieve the real label and return it. And if it's not in my data set, I return 0 as the default value. So what are the decision boundaries on this space, on the space of feature 1 here and feature 2 here? My model returns 0 almost everywhere, except on the 3 points that are labeled to 1 in my training set. So if I take any point in production and receive this point here, the model will return 0 because it's not part of my training data set. The empirical risk is 0. It's an optimal model, but the real risk is 0.5 because the area here inside, the true boundary is 0.5, and the outside area here is also 0.5. So if I look at the errors made by the model, all the surface associated to label 1 here is assigned by the model to label 0, so I have 0.5 errors. And I have already a huge gap between the two. I have an example where a model that is optimal on the empirical risk is not optimal at all for the real risk. And this is called overfitting. This is really the main problem that you will have to deal with when you're training models, is that there will be a discrepancy between the risk, the real risk, and the empirical risk that you can evaluate on your data set. And so we will try another more clever model called nearest neighbor. So for nearest neighbor, if I receive one new data point, let's say this one, where the arrow is, I will look in my training data set. I will find the closest point to this one. So this is this point which is in my training data set. And I will return the label associated to this point. And now the decision boundaries will be more interesting. I will have a partition of my input space. And you can see here that this is the decision boundary where if I'm on this side, all the points in this side are closer to this point than to any other point in the image. So this is what this area means here. The yellow area here are closer to any of these 3 points than any other points, etc. And you can see that I computed by hand. Of course, it's not the exact value, but the real risk is smaller because here I have an error. I assign green label 0 to a label 1 area. Here I have an error, here too. This part I have a big error, and here too, and here. But the decision boundaries seem much more interesting than the lookup table. And if I add a new point here, you can see that the decision boundary are adapt very, very quickly, very efficiently. So what can, just to review a little bit the concept, so the main question is, these two quantities will be closer, will they be close or not? And in fact, it will depend on the number of examples in my training set. If I have only 4 examples, this is an estimation problem. I'm trying to estimate a quantity measured over an infinite number of examples with only 4 examples. There is no way statistically that I can estimate this quantity with this quantity. It's called the estimation error. But there is also another kind of problem that can happen, is that I can choose a wrong hypothesis class. So my learning algorithm will look at this H, all possible model in this H here, and if I'm using bad model in this H, it can find models that will minimize the empirical risk very, very easily, like with the lookup table, but these models will not generalize. And this is very important to specify well the hypothesis class here. Another type of model is linear model. So a linear model will take data X. Here it's 2 features, features 1, features 2, and we will do the dot product between some parameters W with this data point. We'll add a value called the bias, and we will take the sign of this expression. If it's positive, we will say label 1. If it's negative, we will say label 0 for this example. So for 2 features, the dot product, this expression is really the parameters W1 times X1 plus W2 times X2 plus B. And let's look at the decision boundary of a linear classifier. It's, of course, aligned here if we use the feature X1 and X2. And this decision boundary cannot minimize the empirical risk. There is no way we can draw a straight line that will classify all the greens point together and all the yellow points together. This model doesn't have enough complexity to really classify well on the training set. And on the real risk, it's not very good neither, because you have this huge part here, this huge area, which is assigned to label 1, but should be assigned to label 0, as is here. And you have also this huge area that have been assigned to label 0 by the model, and where the real label is label 1. So this model is underfitting the data. I don't have a good empirical risk. And if I add 1 data point here, you can see that I cannot do much better. Oops, sorry. I cannot do much better because the complexity of the model is not enough to capture it. So now we've just seen 2 very different type of hypothesis class. We saw also the lookup table, but it's not a good model in any way. We saw the nearest neighbor classifier and the linear classifier. For the nearest neighbor, when I deploy it in production, I must remember all the points in my data set. It's called instance-based learning. So I need a lot of memory to be able, and after that I need a good algorithm to find quickly the closest point in my data set. And for this classifier, we can see that the decision boundaries are complex and sensitive to new examples. For linear classifiers, we are using 2 parameters, 3 actually, W1, W2, and B. And once I have good values for these 3 parameters, I don't need the data set anymore when I will deploy the model. I just need these 3 parameters which encode all the knowledge from the training set in the model. And so the decision boundaries are simple, but also they are robust to new example. It's not by using new data point, having bigger data set, that the linear classifier will have better performance, because the complexity is not enough. For deep learning model, they are parametric, but they have a lot of capacity. They have a lot of complexity, and they can almost overfit any data set that you can provide to this kind of model. So they are but decision boundaries are very complex because they have a lot of parameters. So just to compare again the 2 hypothesis class, we will say that the nearest neighbor have an estimation error because probably the nearest neighbor will contain the true data distribution, this D that we are trying to estimate. But if we don't have enough data, then the decision boundaries can vary a lot. There's a lot of variance according to the data that I'm using in my training set. If I'm using linear classifier, then I have a high bias because probably the data was not generated by a linear classifier model here, because I cannot minimize the empirical risk. And so there is a high bias associated to this model here. And if I add new data points, I will not improve the empirical risk. I will not decrease it.